Well, thank you. Thank you for putting your emails into the chat box. Thank you for that. So we're going to go ahead and do our midterm 1 review again for chapters 1 through 6. And Lydia so nicely has offered to talk to us about chapter 1 again for our first part to remind you of all those things. So she'll kind of give us the basis of everything we talked about so far. So I'm going to go ahead and give it away to her so she can talk to you guys about chapter 1 and collecting data.
All right, hello everybody. All right, so we're gonna start with just the basics here. Statistics is basically all about gathering information, and you gather that information about your population through samples. The way we measure this, we measure populations through something we call parameters, and samples are measured through what we call statistics. There's a chart on the next slide that can show you that. But basically, since you can't measure populations, it's very difficult to do. You measure your population, you make inferences about your population through sample statistics, and that's a much easier way to gather information about the people that you're trying to make inferences about. So here are some of the symbols that you guys should probably know for the exam. This chart is pretty helpful. So it shows basically just the sample statistic and the population parameter. This is how we measure them. The symbols we use to measure them: mean, proportion, variance, and standard deviation. So those are all very good to know. All right, so variables. So here are two types of variables. I know that you guys do categorical and quantitative, but these are a little bit different than those. These are basically the variables that we use to help answer questions. So in every question you have about a certain subject or topic that you're trying to find information about, there's always an explanatory variable and a response variable. The explanatory variable is the independent variable and is what we are changing, and it predicts the outcome, which is what happens for the response variable. That is what we're measuring, also known as a dependent variable. So let's just say, do the hours spent studying affect your test score? The hours would be your explanatory variable, and we're testing and measuring the scores that you got in your exam. So independence and dependence here. Independence the variables are unrelated. We use randomized comparative experiments to measure these, which randomly assign them to different conditions of an experiment, which makes it more reliable in the end. They do not affect each other, whereas in dependence they do affect each other. And we use paired and matched paired experiments, and a lot of the time the subjects are the same in both of the groups of the experiment.
Yay! Okay, thank you so much, Lydia. That is a perfect segue into our second and third chapters here. Lydia gave us a nice background of basically everything that we are going to be talking about from here. You know, it's important to know about those samples and parameters and statistics and populations in order to, utilize the data that we do have in the different tests that we have learned about. So let's talk a little bit about when we're describing data in general. So remember, Lydia talked a little bit about the variables. So remember, we do have two different types of variables. We have our categorical and our quantitative variables. Our categorical are going to be those with names or labels, so anything that really doesn't have a value attached to them, things that are categories, like on Family Feud when they're like, category is something. Or like that game when you played Concentration 64 and then you say category, names. Maybe no one has no idea what that is, but that's something to think about. It's something that has to do with it has like a name to it. It doesn't have consistent differences between the groups because they are labels or names there. And then the two different types of categorical variables, we do have nominal and ordinal. And nominal just means that they're categorical variables without an order to them. and ordinal does have some sort of order to them. So one of the categories is, higher in the hierarchy than than another. And then quantitative, we also call them measurement variables because they do have numerical values attached to them, and they are placed in a meaningful order because numbers always are in a meaningful order. 6 is always going to come after 2, that kind of thing. So yeah, we call them quantitative, numerical, measurement. They're all the same type of variable there. And then so the 2 different types of quantitative, we do have discrete and continuous. So discrete are going to be data that can only take on a set number of values. Basically, they cannot be broken apart. You can't choose, any number between the minimum and the maximum. There's only certain numbers you can pick. And then continuous means that it can basically take on any value between that minimum and the maximum. So any decimal doesn't matter as long as it's within that range between the minimum and the maximum. You can use, that's what a continuous variable would be under quantitative variables there. Okay, so these are different ways that we can display these quantitative variables. So after you decide that you have a quantitative variable, you can either display it in a box plot, a histogram, a dot plot, or a scatter plot. So we'll talk about the first 3 here. So our box plot here, remember, is a good way for us to view basically the different quartiles of our data and our middle 50%. So here we have our middle 50% is represented by the box. Our median is this line here. This is going to be our upper 25%, and then down here this little line is going to be our lower 25%. So as you can see, the 50 plus these two 25s is what makes up the 100% of our box plot. And then you just have your max up here, and your minimum is down here. And then your histogram basically is showing you the frequency of each quantitative variable. So this is showing you the frequency of each age that they're given here. So the frequency of 24 is represented by the height of this bar in the histogram. Bars do touch in histograms because they're continuous, and the fact that the numbers can overlap in that case. So that's where we get that from. And then a dot plot is literally the same idea as a histogram, showing you the frequency of these quantitative variables on your x-axis, but the difference in a dot plot is that each dot is representing one of your observations instead of all of them being stacked together in a bar in this case. And then to talk a little bit more about scatter plots, basically, so once again, we still are talking about quantitative variables, but scatter plots, we're talking about 2 quantitative variables. So remember what Lydia said, that we have our explanatory variable and our response variable. So remember, explanatory is going to be our independent, and then we do have our dependent variable here for the response. Wow, I didn't think I could write sideways. That was good. Okay, so remember, our explanatory variable is going to impact our response variable. Our response variable is dependent upon what happens with the explanatory variable. So basically, you want to read scatter plots in terms of, what is going on here, and the fact that what's the direction, what's the form, what's the strength, and are there outliers. So your direction is going to be whether it's positive or negative. So from left to right, do we see a positive trend or a negative trend? So for example, here from left to right, it's going downwards. So I would consider this one negative. Our form is going to be, does it look like a line or does it not look like a line? It's pretty self-explanatory. If you had something that looked like this, like a parabola type thing, that's going to be nonlinear. So in this case, I would consider it linear because this does look somewhat like a line. And then our strength is going to be weak, moderate, strong. You can also kind of combine these like, moderately strong, that kind of thing. But so those are kind of our 3 categories, though. Our main categories is basically showing us the strength of these, of these together. So we either have, if they're weak, then they're going to be really spread out. Moderate, they're pretty close together. And then strong, that's going to be that they're really, really close together. So this one I'd consider, in between moderate and strong, because it's not like completely, lined up, but it's definitely pretty close. So I'd say it's between moderate and strong there. And then outliers would just be if you had an observation that was super far out from the original data. So if I had something over here, I'd be like, what are you doing? Like, so that's like no bueno. But in this case, I would say that we don't have any outliers in this one, as long as, we don't have this here. So that's how you read a scatter plot. Remember, 2 quantitative variables. One is your explanatory, one is your response. Your explanatory variable is independent and it's not affected by anything, and your explanatory variable is what explains your response, as that is the dependent variable on your y-axis there. Alrighty. Okay, so then I'm talking a little bit more about outliers. We have the IQR method. And remember, on our box plot here, when we are talking about our IQR, remember that's going to be the interquartile range. So that's going to be our middle 50% of the data. Okay, so that's from here to here, our middle 50%. So our IQR is basically just showing us from the range from Q1 to Q3. Okay, so from here to here. And that's why you find it, IQR, you do Q3 minus Q1. So technically, this is the max of your middle 50%, and then this is the minimum. Same, it's the same idea of a range in general, except it's the inner quartiles because it's within the quartiles. And then IQR method is just another way to identify outliers. It's just creating an area around Q1 and Q3 that's saying, if the value that you found surpasses these, then we're going to consider it an outlier there. If it doesn't, then we're not going to consider it an outlier. But it does just kind of create a boundary that'll show anything that's out past this, we will be able to consider that an outlier. It's just a more objective way than just kind of looking at a graph and being, this looks kind of far out, maybe it's an outlier. It's kind of saying, no, it has to be, past this point in order to be considered that. So that's just a more objective way to find your outliers. Okay, and then this is important. I think a lot of people like writing this on their cheat sheets, and I know I did when I took this class. I think I only got a cheat sheet for the final, though, so take advantage of getting it for your midterms. So that's exciting. So you basically can look at these in the way of what is the relationship between our mean, median, and mode in different shapes. So these are basically distributions of quantitative data. So remember, our quantitative is going to be our measurement data, and this is basically ways that we can display it. So if your display looks symmetrical, so if it looks the same on each side here, then our mean is going to be equal to our median, which is equal to our mode. So it basically means that everything is in the center here. And remember, your mode is like your most commonly occurring value. So you can see it's the highest point on the graph, which just happens to be the middle. So that's why it's also equal to the median, which is, your middle position between your numbers, and then your mean is your average. Didn't mean to cross it out. Your mean is your average, so that's where that comes from. And then skewed to the left, just remember your mode is always going to be your largest, and your mean will be your smallest here. And then skewed to the right, your mode will be your smallest, and then your mean will be your largest, because skewed to the right, here we have more spread on the right, so we're going to have a larger mean because there's more spread here on the right. And then in comparison to on the left here, we have more spread to the left. And then since we have more spread to the left, that means that our mean is pulling it here to the left, and that's why we have so much more spread down here than in comparison to up on the right side. All right. Okay, 5-number summary. Basically, all this is talking about is another way that we can kind of summarize our data. And this definitely goes along with box plots. I've probably drawn a million of these. You guys definitely get this by now. But basically, our 5-number summary is kind of based off of this. So we have our minimum at the lowest, and then our maximum, obviously, at the highest. And then we have our different quartiles, Q1, Q2, and Q3. And then keep in mind that this middle line is going to be our median. And basically, this is how we are able to do this 5-number summary, kind of decide what these values are, what they're meaning. Remember, Q1 is our 25th percentile, Q2 is our 50th, and then remember 50th percentile is always going to be our median here, and then Q3 is our 75th percentile. So remember, percentile means that percent, or what percent of the data lies at or below the point that you have. So for example, for Q1, we can say that 25% of the data lies at or below Q1, okay? So what I'm basically talking about here is going to be all this area in here. Okay, so that's basically what that is. Our range is going to be our maximum minus our minimum, and then our interquartile range, remember, is basically our maximum of our middle 50%, and then minus our minimum of our middle 50%. So your range is just talking about, you know, the area between the smallest and the largest, and whatever that amount is in between there, however many values are there. Okay. This will be on YouTube. So if you go onto the Review Session Central page on your, like on the actual like internet page of this class with all the online notes, there's a link to my YouTube like page, whatever you call it, channel, I don't know. And so after we do this, I have to like export it and everything, but then I uploaded it, and I'll upload within like an hour. I usually get it. Look at Maria. Wow. See, she knows where she knows where my YouTube channel is. Yeah, so this will be posted, as well as my recording from Tuesday, was it? I think, yeah, from the other review on Tuesday. And same with all my other, oh, you subscribed to me. That is just so nice. I didn't think I'd ever have a subscriber on YouTube. I like totally didn't know what was going on with YouTube. I was just like, I didn't know, because we used to do this with Blackboard, and then we started using Zoom with the whole video and everything, and I'm just like, oh, now I gotta see how weird I look, and oh my gosh. But yeah, so I will export this. So it takes a little bit longer because it's not just like since it's like a video or whatever. But same with, you know, if you want to, I always suggest that, you know, when we're going through the midterm review, to kind of decide, you know, which one of, if you see a chapter where you're like, I totally forget what that was, or, you know, I need to review that, go back to my actual 2 reviews for that specific chapter. There'll be a Thursday review and a Sunday review for whatever chapter that was, and that'll give you more in-depth, you know, review of it, because we definitely go through like all of it more in depth there. So, which should be helpful, because yeah, we're kind of just, you know, skimming the surface here and going over all the different topics that we have talked about basically up to this point in the semester. So but yeah, my YouTube channel has all this stuff, and I list in each one in the description like what topics we talk about, so that might help you to guide, yeah, of course, that might help you to guide, you know, where you're able to, like, if that's a video you want to watch or whatever. So I'm trying to find a way to like put which parts of my video, like, I talk about which things, but I'm not that high tech yet. So oh, thank you. I try. So yeah, I definitely I'm trying to figure out a way to make it a little like clear, so you don't have to go through the whole video and try to find it, but I'll work on it. If you guys have any suggestions about anything, you're more than welcome to tell me. Obviously, like, don't think it's like bad. Like, obviously, like, I do these for you guys. This isn't for me. I'm not doing this, you know. So yeah, please let me know if you guys need anything, you know, done differently, if something's helping you more than something else. I'm more than happy to, you know, switch things around. So please let me know at any point. But yeah, so that being said, let's talk about the empirical rule. I love the empirical rule. Super fun, super cute. So we have, this basically is talking about when we have normalized data. So we have to have a normal curve in order to use the empirical rule. So it's basically saying that if you have a normal curve and your data is approximately normally distributed, you can use this empirical rule to discuss what % of the data lies within how many standard deviations of your mean. So in this case, this would be if we had a mean of 0 and then our standard deviation of 1. So, you know, when we go out plus or minus 1 standard deviation, which is represented by these lines here, this is just showing us that plus or minus 1 standard deviation, we have 68% of our data within this. So this shaded part that I just shaded is going to be 68% of our data that lies at or between plus or minus 1 standard deviation. Okay, so that's the main idea there. And then if you were to kind of go over another one, if you were to go for plus or minus 2 standard deviations, it's talking about this entire thing. So including that 68%, that all of this is going to be 95%. So hopefully you get that idea. I know it's just kind of hard to draw. That probably makes no sense at this point, but this is going to be our 95% of our data. And then, the next thing is obviously our 99.7% of the data. So that's all the empirical rule is saying. So if I were to draw a curve and I had, let's say that my mean is 10 and my standard deviation is 2, and I were to draw a curve like this, and I drew values here, and I drew 14 and 10, 6, mental math. So if I drew this, what I could decide is that this is 95% of my data because it's plus or minus 2 standard deviations. So 2 standard deviations down from 10 would be 2, 4, so it would be 6. And then 2 standard deviations up would be 2, 4, 14. And then that's how the empirical rule works, because it's saying that if our data is normally distributed, that we have 95% of our data lying within plus or minus 2 standard deviations here. So this is our minus 2 standard deviations, this is plus. So then we're able to say that this is 95% of our data. Yay, empirical rule forever. Okay, so now we're going to talk about categorical data display. So remember, all that we've talked about so far has been quantitative, so our measurement variables, but these are going to be our categorical data display. So this is going to be talking about our different labels. Remember, they don't have values associated with them. But we are, talking about how frequently they occur, which is, obviously a number, but the categories in general and the variables themselves that are categorical don't have values attached to them. So we have bar graphs, bar charts here, and remember they don't touch in this case. Histograms, remember the bars touched. In bar graphs, the bars don't touch, and the only difference here between like these two and this normal bar graph on the side is that we have 2 variables for our segmented and stacked bar charts, or in our side-by-side bar charts. So they're both just showing 2 variables here, 2 variables here, and they're both, remember, categorical variables. And it's just showing them both on the same graph. So all it is here is that they're stacked for the first one, and then on this bottom one here, they're next to each other. That's the only difference. So yeah, you're able to show 2. So here we have our 1 categorical variable down here, and then our other one is going to be represented by the different colors. So yeah, that's that. Two-way table is another way to display categorical data. And basically we can show, so in this case we have gender, and then we have favorite sport to watch on television. So those are going to be our 2 categorical variables. And then categorical. So, and then in this case, we're able to see, the intersection between these to show, what the relationship between those 2 categorical variables are, dependent on the specific values that you get. So you're if you're looking for amount of females who like baseball, all you do is find the intersection between females and baseball, and then you get 45. So that's just a way to read two-way tables, which remember are for categorical data displays. Yep, you can also call that a frequency table because yeah, it's showing you the frequency of each categorical variable. So that's a good question. And it's the same idea that you can, you can also kind of, I think you can use frequency tables. I'm trying to think. With frequency, you can use frequency tables, I guess, with one categorical, one quantitative. But yeah, you can also, this is also discussing a frequency table because it is saying, the frequency of this being a favorite sport and the frequency of, a male liking this or a female liking this or whatever. So, so yeah, that's another way to describe it. That's a good question. But They're both just still talking about two categorical variables in this case, but good question. Way to be thinking. Okay, so our other way, so this is what I was just talking about, so you can display, if you're trying to mix it up, like as if it wasn't enough to just have one quantitative and one categorical, now we can just put them together because we're crazy and we're trying to do something cool. So here we have our quantitative and categorical variables together. So we can basically remember that, you know, box plots, dot plots, and histograms were all quantitative. They're all going to be our quantitative displays, but then the side-by-side situation and then with groups is where this categorical, like the categorical groups come in. So, you know, if I were to show here, these are going to be my categorical variables. Here's my categorical variables, and then location, here's my categorical variables. And then while my quantitative variables are going to be like my frequency of improvement, my length, and then here my age. So that's basically showing you the difference between having your categorical variable and, you know, the different parts of that, and then your quantitative variable. So in this side-by-side box plot here, we do have our categorical variables of gender, and so we have actor or actress, so men or women, and then our quantitative variable is going to be age, so you know, how old they are, and then you're able to compare them in that way. So that's what that is if you want to combine the two. Okay, risk and odds. So I know this is a little tricky of a concept. And also feel free to ask questions throughout, like I said before. You know, definitely stop me if something's not making sense. But risk and odds are basically, the situation is they both describe the likelihood of an event happening, but you do interpret them differently. So as you can see, they both determine the likelihood of an event because our numerators are the same here, because the number with the outcome is going to be our numerator, but the denominator is what's changing our interpretation. So for risk, you're dividing your number with the outcome by the total number. So that's why it's saying the number with the outcome divided by the total number. So that's your risk, the probability that event will occur in general. You know, so that's like if you hear something, you know, like the risk of blah, 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 that's basically where that comes from. It's just saying the risk that something would happen in general. If you realize, you know, it is the same proportion that we use for proportions and probabilities, you know, it's the number with the outcome divided by your total number of outcomes in this case. So, and then odds is talking about basically the probability that it will happen versus not happening. So this versus not happening comes from our denominator here, where we talk about the number without the outcome. So that's how we're able to compare the two. So, and then another way to put it is if you're given risk already, if you're given that value, then you can use this bottom equation here. Because if you think about it, remember, our risk is the same thing as our number with the outcome, and then 1 minus risk is going to be the number without the outcome, if this makes sense. So those are just two different ways we can describe likelihood of events happening. I need water. Okay. Okay, combination of events. This was a pretty long chapter, pretty in-depth because there's a lot of these. So like I said, check out my video for this one if you're confused about these and want a deeper explanation of them, because we do go, you know, through each one individually, but I will just kind of summarize them in the fact that you know, you want to make sure you understand the different symbols that we have. Our probability of A and B is this upside down U, and then I always draw from my union. This is how I remember union. It's a probability of A or B happening. So probability of A union B. So if you think about, if you have a little dude here, and he's just like, what is going on? So he's really confused, okay? Bear with me. This is going to make a lot of sense. Probably not. Okay, so he's just really confused. So he's over here like, IDK. He's like, what's going on? So if we look at this, he's making the little sign for a union because he doesn't know if he wants to decide between this or this. So that's why it's or. So that's a way to remember a union. People from other semesters said it was helpful. Other people said I was crazy, but that's how I remembered it when I took statistics. So, so yeah, that's another. Oh, okay, cool. I'm glad you like it. Yeah, so that's my little dude. You can draw him on your cheat sheet. Definitely check him out. So he's, or it could be a girl. I don't know. There we go. Got some hair on us. So yeah, that's how I remember probability of A or B is a union, because as long as you, I mean, it kind of makes sense that it's a U for the symbol, you know, because union, and then, but then you want to make sure you understand that definition. So that's basically why I use my little homie over here, because he kind of shows me that definition there. So that's that. And then intersection, remember, is our probability of A and B. So if we have A here and B here, it'll be this intersection part here of our Venn diagram if we're using that. And then complement is basically everything except for A. So remember, if we have our probability of A here, our complement is going to be here. So that's going to be everything except for A in this case. So that's where we get that's a probability of not A. And then conditional is going to be our probability of A given B. That's what this line means. You know, we interpret that to mean given. And that's basically saying that B has to happen before A happens. So that's all that's talking about. And then we have independence, which is just saying that they're not related. Lydia talked to us about this earlier and did a really good job explaining the fact that when things are independent, they are not related to each other. They don't affect each other. They're not influenced at all by each other. If you're an independent woman or man, then no one affects you, and you just do you, you know. So that's independence in that aspect. So I don't know why I have this down here because we already talked about it, but so yeah, basically that's independence. So like I said, if you want a more in-depth review of those, go ahead and check out the video. I'm pretty sure this is lesson 3, maybe, or 4, I don't know, but like I said, each video has a, yeah, I know, yeah, Venn diagrams are definitely a very good way to visualize these, and actually I do have examples of the Venn diagrams for each of these that it makes sense for. Yes, thank you, Maria. Yeah, so chapter 3. I never know what the chapters are. I just know what we're talking about sometimes. So, but yeah, the Venn diagrams are a good visual. I'm a very, well, theoretically, no one is a visual or like auditory learner. We're all a mix of both. But you can be like more so of one, and I think I'm more so a visual learner, so I do also like Venn diagrams. I think they're a good way to display, especially things like this when you're looking for relationships between two things. And you'll see I often use color coding because I think that's helpful too. You know, because sometimes when I'm thinking about things, it like helps me to remember, like, oh, that was in this color, and the other one was that color. I don't know, but that is about combination of events, talking about those two. And remember, these are categorical. So that's something to keep in mind too. You want to make sure you understand, you know, like scatter plots are 2 quantitative variables, and then combination events are talking about categorical variables, so on and so forth. Just make sure you're able to decipher the difference between those. That's why it's important, you know, to understand those beginning chapters of, you know, what type of, like, what a categorical variable is, what a quantitative variable is, in order for you to go through and actually be able to, you know, pick them out then when we go further on into the chapters. So. Okay, another example here, we have correlation. So this will be when we have 2 quantitative variables. So with 2 quantitative variables, we are going to have, we're talking about the strength and direction. So it's 2 different parts to correlation. And so our strength is going to be represented by the number, and this number is always going to be between -1 to 1. And then our direction is either going to be positive or negative. This is positive, not a T. So that's the main difference here. You basically take this number of -1 to 1, and, you know, the direction will be technically, you know, between I mean, it'll be shown if it's negative or positive, but you have to have a linear association to use correlation. If you don't have a linear association, it doesn't look like a line, then you cannot use that. And it is 2 quantitative variables, so remember these are measurement variables. And then this is saying absolute value of R, because remember I said it could be between -1 and 1. But in this case, if you're doing the absolute value of R, you can have, 0.8, and, the absolute value of -0. Yep, it's similar. Yeah, because it's showing, it's similar to it. It's not exactly the same because Cohen's d is talking about effect size. So this correlation is just talking about, with the numbers, are they correlated or not. Cohen's d is talking more about practical significance. So it's a similar idea because they're like similar numbers, obviously, and you interpret them in a similar way, but this is more involving the quantitative variables and numbers. Cohen's d is talking about like more practical significance. So it's saying, is this, yes, yeah, correlation is a relationship between those 2 quantitative variables. And then your effect size with your Cohen's d is basically saying, is this a big enough is this a big enough effect size to say that this is like practically significant in real life? So that's the main difference there, but they are similar, especially with the numbers here, and how you interpret them, because, so if we have -0.8, our absolute value of this is going to end up being 0.8. So like that's why we're talking about, that's what it talks about here. And this is going to be a very strong relationship because, so this is absolute value. It's not 1 of -0.8, but this is going to be a very strong negative relationship if we're talking about this -0.8 here. So that's the main idea there. Okay. Oh, okay. Chapter 4, confidence intervals. Whoop, whoop. Okay, so our confidence intervals, remember, are the range of our data. So this is going to be when we're talking about, we're trying to estimate an unknown population parameter. So we're going to take a sample and keep taking, randomized samples from it, and then we're using whatever we get from those samples to estimate where we think that this unknown population parameter is. So it's going to be within a range. So we're going to have a lower bound, and then between that and then an upper bound. And then within this, we're trying to say that we think that the population parameter that we don't know is within that. Our point estimate is always going to be a sample statistic, so we're going to have p hat or x bar. My one student in person always says x bar. Don't ask, but that's another way to remember it. He does that every single time I mention x bar. So that's they're both sample statistics, remember, because we are using these samples. Like Lydia said, we do use our samples to make inferences about our population. So so that's always going to be our center of the confidence interval. So our center is either going to be our p hat here, or our center is going, that was horribly drawn, but, or our center is going to be our x bar. So that's the main situation there. And then our multiplier for example, a 95% confidence interval, we use 2. You'll also see it as 1.96, but we often use 2. It will change dependent on the confidence interval, but we do just often use 2 for that. And our standard error is a standard deviation, but it's going to be the standard deviation of our sampling distribution. So remember, we're using these samples because we're trying to estimate this unknown population parameter. So all this stuff in our confidence interval equation is going to be from a sample, hence why we use p hat or x bar for our point estimate. And then our standard error on our right side is going to be the standard deviation of our sampling distribution, because we don't know the actual standard deviation. And then once again, remember the connection between, if you have a categorical variable, you're going to be using proportions. And then if you have a quantitative variable, you will be using means. So that's the biggest idea there. And then also remember that if you increase your sample size, then your confidence interval is going to be more narrow. So it's basically saying that you can be more confident that your population parameters in with a smaller distance. So if you think about it, we always want to have a larger sample size because that'll be more representative of our actual population. And our confidence interval being more narrow is good because if you think about it, if we say, you know, we're 95% confident that, let's say I had a sample size of like 10. I say, you know, we're 95% confident that the population parameter lies between, you know, 2 and 600, okay? So that's my confidence interval because I had a really small sample size. So I have a large confidence interval and it's wide. But let's say I increase my sample size to like 1,000. Yes, your standard error increased sample size decreases increased sample size decreases your standard error because you have a less chance of making an error there. And so that also, remember, standard deviation, standard error is your spread. So if you think about it, you know, when your sample size increases, you know, your spread's going to decrease. So your standard error is going to decrease. And then also, you know, how narrow your confidence interval is going to decrease. So with that other example, you know, if I was to increase my sample size to like 1,000, then I can say something, you know, if I were to calculate, I could probably say something like, you know, I'm 95% confident that my confidence interval or the population parameter lies within or lies between 2 and, you know, 50 maybe, you know, so I can make it more narrow because I have a larger sample size and it's able to be more confident that it's in a smaller range of data, which is good. Easier to be more accurate there. This is just relating to the fact why we use the multiplier of 2. Off of, for a 95% confidence interval, because it goes back to the empirical rule because we love it. And so as you can see here, we have our mean of -2, our mean plus or minus 2 is what I have highlighted here in gray. And then here we have our 95%. So that's just showing where we get that multiplier of 2 from, because we are trying to take our standard error and multiply it by how many standard deviations it would be out to make 95% of the data and to make a 95% confidence interval. Okay. Okay, so and then when we're interpreting a 95% confidence interval, we're going to have the idea of how confident we are, basically that our population proportion is between our lower and upper bound. Okay, is the standard error normally larger with a 99% confidence interval? So it's more so your standard error is more so dependent on your sample size. Because if you have a 99% confidence interval with a small sample size, you're going to have a larger standard error. If you have a 99% confidence interval with a small sample size, you're going to have a larger, did I just say that? The other way around, but they're inversely related. So yeah, it doesn't necessarily have to do with the percent of the confidence or your percent of confidence. It has more to do with, you know, your sample size, because when you calculate standard error, you're using your sample size to calculate it. So that's why it's inversely related, because it's usually on your denominator. So as your numerator increases, your actual, you know, output is going to decrease. So that's a good question. But yeah, so make sure, you know, you understand that our standard error is more correlated with our sample size instead of our, you know, percent of confidence here. So in this case, if we're interpreting this 95% confidence interval, we always start out with, we are 95% confident that the population, so remember, we're making a claim. We just took a bunch of samples and we got this lower and higher bound, and we got these from a sample, from our samples, and then we're using these samples to make an inference about our population. So we're 95% confident that the population, and then if we're talking about proportions, so this would be for categorical variables, or mean, which would be for quantitative variables, in question is between our lower and upper bound. So that's basically just saying, you know, after you get these two variables, after taking all your samples, you get your lower and your upper bound. That's how you're able to make this interpretation about that confidence interval that you just got here. And that's just an example of lower bound and upper bound here. Higher bound, whatever. Okay. Okay, bootstrapping, everyone's favorite. So bootstrapping is basically just talking about, you know, are we going to take samples and continue to take samples, or are we going to take samples and replace them before we take another sample? So the main point of bootstrapping is that if we don't have a large enough sample size to keep taking samples out without replacement, we're going to use replacement to kind of alleviate that problem of having a small sample size. So two different ways of doing it. We have our standard error method and our percentile method. So standard error method, remember, is talking about our spread. And remember, when we're talking about that, we do have to have an approximately normal sampling distribution in order to use our standard error method and talk about that. In order to show that empirical rule with the 95% confidence interval, because remember, we also have to have normative data to use that empirical rule, which is what the standard error method is based upon. And then our percentile method, we can use that no matter what, because there's always going to be a percentile for each, or there's always going to be like a place for each percentile in this case. So that's where we get that from. So those are just two different ways you can do bootstrapping. Ooh, hypothesis tests. How much fun. I love hypothesis tests. So when we're writing hypotheses, so these are this is the beginning steps when we're trying to figure out what's going on. We're going to always have our null hypothesis. It's always going to look like HO, and then it's going to have either mu equals, and then your value, or P equals your value, which is going to be between 0 and 1. And this can really be like any number. So in this case, these are basically your two options for writing your null when you're talking about one variable. It's different, obviously, if you have like a P1 and a P2. But if you have one variable, these are your two ways that you can write your null hypothesis. Remember, it always has to have an equal sign. We'll never have anything else besides that. And on the contrary, we have our alternative hypothesis where there's going to be some sort of change going on. So for our alternative hypothesis, you can either have mu, and remember, we're always writing, because this is what we're making inference about the population. So we're going to use population symbols. As Lydia showed us earlier, those the list of the population symbols that we can use. So remember, mu and P are population symbols for mean and proportion populations. So you can either have basically mu is greater than your value, mu is less than your value, or mu is not equal to your value. Or you can have that P is less than your value, P is greater than your value, or P is not equal to. So basically, these are your options for writing your alternative hypotheses. These are like totally basically everything that you can use when writing these. So remember, we're never going to have an equal sign in the alternative. We have one of these three, and then we'll always have an equal sign over here for the null hypothesis. Okay. Okay, so when we get a p-value and we are deciding, what are we going to do with this? Basically, we're trying to decide how big is this p-value and what does that mean. So remember, a p-value, we always assume that the null is true. That's like our assumption always. We're assuming that there's no change. And then the biggest thing here is to decide, if our p-value is small enough in order to reject our null hypothesis and kind of change that assumption. So if our p-value is greater than alpha, that's saying that there's a high probability that or a higher probability that we have made an error, that something's going wrong here. So remember, our significance level is our alpha level. So if p-value is greater than alpha, we're going to fail to reject that null. So we're still going to keep our assumption that the null is true and that there's no change. And then if our p-value is less than alpha, we will be able to reject that null hypothesis. So this will be in favor of our alternative, which remember, the alternative is talking about having some sort of change. So we're in favor of that if our p-value is less than alpha, because it's saying that there's a less probability that we made an error there. Speaking of errors, here they are. So our alpha, remember, that's what we just talked about. It's our significance level, and that's our probability of making a type 1 error. That's why we want it to be small, that's why we want our p-value to be smaller than that, because that means that there's a low probability that we made a type 1 error there. So remember, type 1 error is going to be when we reject the null when the null is true. So we're saying that there is a change when there's not. So we're rejecting the null when the assumption that we made initially was actually true. And then for a type 2 error, we're going to fail to reject the null when the null is actually false. So we're saying that there's no change when there actually is a change. So that's a type 2 error. And we denote that with beta. So those are just different symbols we use to represent those. And I just showed this table down here, so it's another two-way table, so you're able to, intersect and see, if, depending on what decision you make and what is actually true in reality on that, on the top there, then you're able to decide if you made a correct decision or if you made an error. So type 1 error, alpha, and then beta, probability of a type 2 error. Okay, and then power is basically just talking about is basically the opposite of the probability of making a type 2 error. So our type 2 error is when, our power is just going to be making a correct claim that there is a change. So our power is good. Our power is saying that you correctly said that there's a change going on. When, your type 2 error is like incorrectly saying there's a change. So saying there's a change when the null was actually true, saying there's a change when there wasn't a change. So rejecting a false null hypothesis. So sounds like a double negative. It's basically saying that you correctly said that there's some sort of change going on. So that's all that power is. It's just the definition of it. And power is inversely related to the probability of making a type 2 error, because the probability of making a type 2 error is going to be beta. And then, if you do 1 minus beta, obviously if beta goes up, your power is going to end up going down in that case. So that's where we get that. Increase alpha, yes. If you increase alpha, then you're decreasing beta. So if you want to decrease your probability of making a type 2 error, you will increase alpha. So that's a good question. Okay, so let's do some review questions. Woohoo! Okay. So I'll go ahead and read these, and then you guys can read through the answers and go ahead and type what you think it is in the chat box, whichever answer you think, and we will go over it. So this first one says, which of the following statements is correct about a parameter and a statistic associated with repeated random samples from the same size from the sample population, for the same population, excuse me. So go ahead, read through these answers and let me know what you think. All right, great job, guys. Absolutely. So our answer is B here. So remember, Lydia told us this from the beginning, that our populations are going to be fixed. And then remember, populations, this is going to be, the measurement of them is parameters. And then for samples, those are going to vary. And then remember, our measurement of that will be statistics. So in this case, our answer will be B here because it's the only one discussing that the values of a statistic are going to vary, which is true. And then according to the sampling distribution for that statistic, that's the only one that's correctly making this claim. So this is not true. Values of parameter will not vary because remember, this is going to be fixed. So that's why A is not correct. And then C says values of both a parameter and statistic. No, it will not. So that's not true. Statistic will, but not a parameter. And then for D, values of a parameter will vary. Nope, already. Womp, not true. So that's why our answer is B. So great job, guys. All right. All right, number 2. So which of the following variables could we use a bar graph to display these? So let me know what you think about this one. Yay! Okay, great job, guys. So our answer is C here because, so remember, bar graphs is how we display categorical variables. So in this case, the only categorical variables here is going to be C. So model car, that's categorical. The rest of these are going to be quantitative. So grades on a final exam, quantitative. Dollar amount, quantitative. And then height is quantitative too. So it can't be any of those because we're looking for categorical variables for bar graphs. Our answer is C. Yay! Good job, guys. All right. Okay, number 3, what is the mode of this pie chart here? So let me know what you think about this one. Good job. Yeah. Okay. It's actually funny. In my notes, I spelled Germany wrong too. I'm not really sure what the situation was with that, but yeah, great job. So our answer is Germany here, because it's going to be the mode is going to be the most commonly occurring one. So in this case, you can see it. The most commonly occurring will be Germany because it's taking up the most of the pie. So that's the piece you want, obviously. All right, cool. Good job. Okay. Okay. A farmer is conducting a study concerning the heights of pigs on the farm. She takes a random sample of 50 research pigs and measures each individual's height in centimeters. So which of the following is appropriate for displaying his data? All right, try this one out. Awesome job. Yep, so our answer here is going to be D, because we are talking about, so random sample, height in centimeters, undo, height in centimeters. This is going to be a quantitative variable. So in this case, these are going to be how you can display categorical variables, but dot plot is the only one that we can display quantitative variables in this case out of these options for. So that's why that's the answer. So great job. Okay. All right, a kindergarten teacher wants to analyze the number of girls and boys in her class that likes vanilla and chocolate ice cream. Exciting. So which of the following is appropriate for displaying this data? Let me know what you think about this one. All right, yep, great job, guys. Absolutely. So our answer is C here, because this is the one that we have categorical variables, but we have two of them, which is, because here we have gender, which is our one categorical, and then we have flavor of ice cream, which is going to be our other categorical. So since we have two, that's going to be our two-way table here. So scatter plot and dot plot, these are for quantitative, so that's a no-go. And then bar graph is okay, but that's only for one categorical, and we're looking for two. So our answer is C. Yay, good job. All right, let's try another one. All right, holding all other factors constant, how does the width of a confidence interval change when the sample size decreases? Try this one. Awesome job, guys. Absolutely. So remember, there is an inverse relationship with our sample size and the wideness or the width of our confidence interval. So if we have a decreased sample size, then our width is going to get larger here. So that's why A is the answer. Obviously, B and C aren't the answer if this is the only one that makes sense. So they do have an inverse relationship here. So that's something to keep in mind. Same thing would go if you increase that sample size, then our width would decrease. So good job. You guys definitely understand that. All right, a few more. I think we only have two more. So a hypothesis test for a population proportion, P, is given below. So if we find that the p-value 0.033 then, sorry, which of the following describes this data set and its conclusion completely with a significance level of 0.05? So try to answer this one. Let me know what you think. Awesome job, guys. Absolutely. So our answer here is going to be D. So we know that this is going to be a two-tailed test because of this not equals to sign. So B is out of the question because that's his one-tailed test. And then because we're using P is going to be for a proportion. So we can cancel out C because that's talking about for a mean, which is not true. And then basically the last thing we have to look at is, what decision we're going to make. So here, our p-value, so 0.033, is going to be less than our alpha, which is 0.05. So p-value is less than alpha. So in this case, we can reject that null hypothesis. So that is why A is not correct, because we're not failing to reject. We are going to reject it. So D is the only one where all the parts of it are correct. So good job. All right, one more. Okay. All right, which of the following symbols can be used when writing a null and alternative hypothesis? So let me know what you think about this one. Yay! Great job. I love the confidence, Maria. Yes, E is the answer. Because remember what Lydia told us, that we can only use these symbols when we're talking about populations. Okay? And then these symbols we use for samples. But then when we're writing null and alternative hypotheses, we're always going to use our population symbols here because we're making hypotheses about that population. So that's why E is our answer, because we could use A or B when writing that. So great job, guys. You did a great job tonight. So that's all I got for you. So obviously you can go ahead and watch this back at the YouTube channel and all the other ones, all the many hours that we've spent together. So our next group review actually will not be until Thursday, because we had our 2 for midterms already this week. So sad we have to go so long. You're very welcome. I know we have to go so long without each other. So sad, but we'll be back next Thursday to start anew, and you'll be done with your midterms. Yay! Hey, thanks. You rock too. Yes. You guys are the best. Raise the roof. Yeah, no, seriously, if you guys, and also if you haven't put your Penn State email in for me, go ahead and do that, please. 11/11. Wish that you guys do great on your midterms. But yeah, let me know if you have any more questions. If not, obviously, you guys are good to go. I don't think I ever put my email up here. You guys can obviously email me. So if you want to email me if you have any extra questions, I'll try to answer them over email. So, but yeah. Okay, cool. Well, thank you. I'm glad you enjoyed. Hopefully it wasn't too painful and boring. Try to make it not too lame. Yeah, Maria, you can go ahead. Oh, well, thank you. So sweet. Thank you. I appreciate it. Hopefully you learned something. Maria, you can go ahead and answer your question, or I can answer your question, whatever you have. That's totally fine.
Okay, I mean, I was gonna type it, but it's too much.
That's okay. No, that's totally fine.
So with the bootstrapping methods,
Ah.
yeah, that's where I'm like, I'm not completely lost, but it's just like I think I get confused with confidence interval.
Uh-huh. So remember, bootstrapping is going to be when we do it with replacement. And the biggest thing to remember with our methods is that our standard error method is going to be when we're talking about like our normative data has to be approximately normal. And then from that, we are going to be able to find that confidence interval there. So that's when we're able to use that equation of the point estimate plus or minus 2 times our standard deviation. Because we have approximately normative data, that's why we can use our multiplier of 2 off of the empirical rule, because remember, to use the empirical rule, we do have to have approximately normal data there. And then for our percentile method, it doesn't matter because there's always going to be a percentile in any type of data, even if it is skewed. So does that answer any part of your question at all? Or are you like, I already knew that?
No, it is. I mean, like, I know you repeat it a lot, but it's just like, I think because I'm just like overthinking it, I'm just like, okay.
Yeah, I know. A lot of statistics, I know, because some parts of statistics are very like, you have to think really hard into it and you're just like, but like, also a lot of it, is simple, and you want to make sure that, you don't overthink it. And, you're making sure that you first think of it, at the basis and then move up from there. Don't automatically assume that it's going to be super confusing, because some of it's very straightforward, because if you think about it, you see statistics, in your everyday life, risk and stuff. That's honestly, if you think about it, risk is very like simple. People get tripped up on that, but risk is very simple. Risk is literally the probability of something happening. Like, you hear that all the time, so it's definitely something that and like I said, I try to say things in like 100 different ways to hopefully that one of them makes sense to everyone, or to, different people. So just try to, listen to all the different ways and then decide, what you think, makes the most sense to you. So it's one of those things that you probably just have to sit down and think about it, and then it'll click. Everyone has that moment where they're like, well, duh, so. Center the bootstrap is. Yes, Ella, that's correct. Yeah, so your center of your bootstrap is always going to be p hat or x bar. And then when you're doing a randomization and you're putting it on that normal curve, like the empirical rule or like a z curve, your randomization, the mean is going to be 0, and then your standard deviation will be 1 in that case.
Okay, cool. Yeah, I think I got it.
Yay! Okay, cool.
I think.
You're welcome.
Thursday, well, whatever it is.
Yes, I know. Whenever I never even know when it's going on, but yes, I will see you then.
Okay, bye. Good luck to everyone.
Yeah, good luck, guys. You can do this. I believe in you. You got this.